All right, good afternoon. Let's start lecture. Okay. All right. We're going to talk about a new material today now. Okay. And so we finished the content static failure analysis for both brittle and ductile material. So now let's look at a new concept. Okay, this time it's just basically it's called design for fatigue loading. So we'll look at basically what fatigue loading is. Okay. So fatigue is a very, very common phenomenon, and that particular happens to all of us every day, and is also a very dangerous thing. So as the news title says, right? The yawning almost killing a man. And then, when you're really tired, when you're really stressed out, and you break down, right? You basically not going to function the same as yourself. So the force in nature is strong, right? So not only humans are getting tired, metals can also get tired too, right? And what if metal get tired? So then what happens? So that's basically what we're going to look at it. Right? So the first concept, what is the fatigue? Right? What is fatigue here? Yeah. As you can imagine, when we're talking about fatigue, basically we're talking about constant, continuous type of loading, type of pressure, right? And type of external, pressure, right, on ourselves, on our body, on our mind. So that's basically the kind of things that we call it fatigue. We just feel so tired. And for metal, it's very similar too. You got to have a certain cyclic type of loading. Okay, keeps acting on the metal parts. Okay, keeps acting on the metal parts. And there are theoretically, there are a different type of basically so-called cyclic loading. Okay, as I listed it here, and we're going to come back to this a little bit later in lecture 2. Okay, but for now, basically you should understand there are basically 3 different types of loading we're going to look at in this class. One is the so-called fully reversed. Okay, so as you can imagine, the loading completely reverts itself within one cycle, okay, and then keeps going. Okay, so it's basically a sinusoidal curve, right? So that's your loading. For the sinusoidal curve, the important parameters that you should remember is one is this amplitude, and we call that sigma A. So this is your amplitude. Okay, and also you have minimum, maximum. So you have a sigma max and a sigma min in it here. So that's fully reversed, or sometimes we also call it completely reversed. Okay, so the wording wise, the same thing, completely reversed. Now this one here is called repeated loading. So repeated loading meaning it goes up but then come back to 0, goes up and then come back to 0. Okay, so repeated essentially means the minimum, the sigma min, is equal to 0. Okay, and then you of course you have the sigma max over here, and same thing, you have your sigma A, okay, the amplitude. And the last one, which is the most general case, is called fluctuating type of loading. Okay, fluctuating type of loading basically means there is a mean value at here. So this is a mean value, sigma m, and sigma minimum, okay, is not a 0. Sigma maximum, okay, of course not a 0. Okay, and then you have your sigma A over here. Okay, so that's called fluctuating loading. So in the future, when you see the wording fluctuating loading or repeated loading or complete reverse loading, and these are the 3 curves that should jump into your mind here. Okay, so what the 3 basically words referring to it here. Particularly for the last one, okay, for the last one here, the relationship between sigma min, sigma m, and sigma max. So your sigma m is actually equal to sigma max plus sigma min over 2. Okay, And the sigma A at here, okay, is sigma max minus sigma mean over 2. Okay, yeah. So that's the relationship, right? And we'll do some exercise later. So essentially, where the sigma max, sigma mean are from are probably from the maximum loading, right? Maximum load force or minimum load force. Okay. Another important parameter, especially when you're using some software for simulation, there is a parameter called stress ratio. It's the parameter, basically the ratio between the value of sigma mean and sigma max. So this one is called stress ratio. Okay, yeah. In some of the software, especially SolidWorks, you will be asked to specify, if you're simulating fatigue loading, you'll be asked to specify what the stress ratio is. So for example, if we specify stress ratio equal to 0, okay, yeah. So what does R equal to 0 corresponds to? Which one does it R equal to 0 corresponding to now? When R equal to 0. Which type of loading condition? R equal to 0, so this is R equal to 0 here, right? Sigma max is not going to be 0. So R equal to 0 basically means that sigma mean is 0. If sigma mean is 0, it's repeated. Okay? So basically you're telling the software to simulate the repeated condition. Okay? Yeah. So how about R equal to -1? And if R equal to -1, well, which case would it correspond now? Fully reversed. Okay? Yeah. Good. Unfortunately, there's no. If R equal to some other random value, for example, 0.3 or something, right? So that'll be this one here, right? Yeah. Okay. So the fatigue loading basically is a loading under either one of this one and here, okay? And with the fatigue loading, there will be this so-called progressive damage or fracture of the material. So I think I'll use a few examples here to illustrate what does the progressive damage mean, or what does the progress fracture means of material, okay, caused by the repeated cycle of stress. So here is an example here, okay. Before we talk about example, the typical fatigue process consists of three stages. First stage, there has to be a crack initiation. And the second stage is the propagation of the crack. And the third stage is a fracture. So the whole part's fracture apart. Okay. And this one here is basically a piece of wire. Okay, it's a rectangular wire here. And then we place that under a so-called scanning electron microscopy. Okay, it's an image of that fractured wire. So what happens is, what you do is, if you can grab any wire, and you probably have done this kind of things many times. So you grab the wire and then you start to bend the wire. Okay. Now in this case, the bending is like this. Okay, the bending is you only bend it to one side. Only bending one side, come back. Okay, not bending downward again. Just bending one side, come back. Bending one, keep doing this, right? Yeah. So that's basically what this piece of wire is experienced. Okay, so experienced one direction of bending. Okay, one direction bending. And of course, after a little while, and then you probably you play this game, and then the piece of wire is just broken, right? Yeah. So if we place this underneath this scanning electron microscopy, and we'll look at basically what happened is the progress here. Okay. This dark area, this dark gray area, is the propagation of the crack process. Okay, and the crack starts at this location and here, As we're going to see, typically the crack initiation, the location will be the location where you have either a discontinuous geometry or where you have a little bit damage, okay, or a little bit piece of basically imperfect locations. Now, in the previous lecture, we learned for the location that has a discontinuous geometry or non-uniform geometry, what's one thing happens at a location in the previous lecture? When you have a discontinuous geometry, stress concentration, right? So that stress concentration will act as a stress riser, and that basically will typically cause this initiation of this crack there. Okay, yeah. So it it's progressing like a basically kind of like a dark sand area here. So there's a waves here. If you look into the another picture, there's a progressive basically crack propagation, and up to this last section here. So basically at that stage, the piece of wire just cannot resist another bending anymore, and it just cracks. Okay, yeah. So that's the process of this fatigue loading fatigue failure, okay? under a cyclic type of loading. Okay, and the other thing that you also should understand here is, okay, this crack, okay, only propagates, okay, it only propagates under tensile stress. Okay. So if you imagine this piece of wire that we're bending, right? So every time when you bend it upwards, when you bend it like that, what type of stress does the bottom half of the wire experience? When you bend it upward, it's what type of stress? Normal stress, and then it's a compressive or tensile? Tensile, right? Yeah. So when you apply a stress, basically let's say this way, and then it's downwards here will be compressive, and that action will not cause any propagation of the crack. Okay? Yeah. Here's another example. Okay, this example here shows a NASCAR suspension failure here. Okay, in this particular case, the fatigue actually initiated the multiple origins. Okay, so there are different locations of imperfection on the parts. Okay, and because of the multiple origins, and then you notice this so-called ratchet mark. Okay, so basically it starts like at different locations, right? One here, one here, one there. So that's why you see this uneven surface at here. But however, at the end of the day, basically everything merge into one plane, and then the parts breaks. Okay, yeah. So this is the same process, just slightly different, basically a progression of the crack. Okay. If we zoom it into really small dimensions, really small scales, okay, zooming into here, so you will see actually the fatigue fractures exhibit distinct features, which is called the so-called striations here. So these marks here, okay, is actually striations. Okay, so it's like basically the wave on the beach. Okay, you'll see the mark left by the waves. Okay, and that's basically the mark left by each cyclic loading. Okay, by the repetitive cyclic loadings caused on the parts. Okay, and they are very small. Okay, they're typically like a 10 to the power of 9 to 10 to the power of 10 to the negative 5 millimeter per cycle. Okay, yeah. It depends on basically the amplitude of the loading. So what I showed you at here is a very ideal case. We are assuming constant amplitude at here, right? Yeah. In reality, your loading condition could be, this kind of loading condition, right? Yeah. So that basically will cause a different type of the pattern for this striation in there. Okay. Fatigue failure is a very dangerous phenomenon. Okay, very dangerous. The reason is it's not like a static loading. For static loading, you will notice that you will see it yields. Okay, you see it yields, right? Yeah. But fatigue loading, it happens very suddenly, and it doesn't show. Sometimes you don't see the phenomenon because it might happen within the parts, right? And if that's the case, then you can't see it, and then you don't know what's going on, and you assume everything is safe, but maybe it's already almost the danger almost going to happen, right? This is an example right here, basically. In 2007, November 2nd, there's F-15 fighter plane here on the regular, I think, a training motion, okay, training practice, okay, and I'll show you a video right here. Okay, basically the airplane crashed, but it really crashed out of nowhere, as you can see the simulation done afterwards. Okay. So that's what happened, right? In the middle of the blue skies, and the plane just broke into two pieces, multiple pieces actually, right? Yeah. And the location of this failure is somewhere around here, and that's the basically close to the cockpit. There is this Langeron area, which I'll show you here. Okay. Yeah. So it's very sudden, very dangerous, right? And nobody expected that. Okay. So, but of course, things happen, and they didn't look at it. What's the reason there, right? So, what they find the reason is because this is the Langeron area here. There is essentially a discontinuous thickness, okay, or a thickness difference over this area, and that thickness difference, maybe due to the machining, or maybe due to basically whatever reason, which is different from what the blueprint specifications is, right? As we just said, when you have a discontinuous geometry, or when you have a non-uniform geometry here, at that particular location, there is this so-called what? Stress concentration. Okay. Yeah. And that's the location which caused this failure to happen, right? So, and they later find a few similar mistakes in 9 other F-15s. So that, which is good. They find the problem. I think the pilots survived. So that, to give you a perfect example, you can find many other examples. The fatigue failure, how dangerous the fatigue failure is. You should think about. You should also think about yourself, right? Essentially, you don't want things to accumulate. Always examine, always prevent these kind of things. So that's what the idea for fatigue loading. How do we prevent fatigue failure happening, right? How do we, or even let's see, how do we predict that when this fatigue loading will happen? Okay, yeah. So it's like this. So you have a cyclic loading here. So every cycle will cause damage, right? Yeah. Then the question probably is, how many cycles can I predict that this part will fail, right? That's another legitimate question. Or even better, will the parts will never fail, right? Because of this fatigue loading. Okay. Yeah. So that's the answer that we want to find out, okay, from this part of the lecture right here. Okay. Yeah. So to find this answer here, before we find it, before we go ahead, let me ask you a simple question right here. Okay. This is actually an experiment conducted by Da Vinci a long time ago. So he has 2 strings. Okay, one is a very long string, and the one is a very short string. Okay, and both string will be a for both string there will be a same weight metal ball attached to the string. Okay, yeah. So here's a question here: which string do you think will fill first? And you let the ball doing pendulum type of motion, for example, right? The longer one or the shorter one?
Longer one.
And why? Yeah, why is the longer one will fill first?
Maybe because the torque from the...
Don't think about from the torque point of view. Think about from the phenomena that actually we were explaining it here, right? Basically, which one will be more subject to imperfections? Right? Shorter one? Why shorter one was subject to more? Yeah?
The longer one,
Mm-hmm.
there's more strain where it could go wrong.
Yeah.
So, like, essentially, there would be more chance of
Exactly.
more.
Yes. Right? So that's basically when you build a part, that's exactly the reason here, right? And sometimes you don't put a very flashy things in here and there trying to make it beautiful, right? It looks better now, but then the added feature will also adds up those imperfections here and there, right? And that's basically why the longer string will actually tends to fill. Okay. So I guess that's the reason sometimes being a short guy is, you're okay, you're better. Yeah. So anyway, now back to this question here, right? We want to prevent fatigue failure, okay? And just like we want to prevent static failure. So we want to prevent static failure, then what do we have to know? Okay, we have to know essentially what is the strengths, the yielding strengths of the material is, right? And then we can talk about how do we prevent that from happening. So for static one, you can do a basic tensile test to find that information, right? Yeah. And we want to go along the same, basically, same along direction there. So if I load the parts with a fatigue loading, right? And then there got to be some sort of a similar strength concept for us to make use of, okay? To compare with the stress. That makes sense, right? So how do we find that strength information then, right? So this is where this, the tensile stress testing, and this is the fatigue testing, basically is illustrated here. It used the so-called RR Moore rotating beam fatigue testing machine. We actually has one of this in our lab, and it used to be a fourth-year mechanical engineering lab. But because this lab is practically so boring, you just set it up and you let it go, right? And nothing really, you let it go for a little while and then the parts will break. So what happens is you have a motor, okay, and attached to the shaft at here. And in the middle of this here, there is a place for you to attach a so-called test specimen, okay? Yeah. So this test specimen is designed typically using certain material and also machined, okay, with a very standard surface finish with also a standard diameter in the middle. Okay, so that's why they call it test specimen. So this specimen is attached in the middle right here, okay, and here you have a counter, basically count how many revolutions has this part being experienced, okay, or subject to. Okay, so you basically apply this one here, and then also attach to the middle here, attach the weight, and I'll show you why you attach the weight here. And you let it go, okay, and after a number of revolutions, and you'll see the part, start to see a crack on the parts, okay, yeah. And if you let it go a bit longer, and you'll see it actually breaks, okay, yeah. So that's what this RR Moore rotating machine does here, right? So let's take a look at this, how it works, the principle behind this RR Moore rotating machine here, right? Yeah. So here is the W. Okay, so basically this is the weight W at here, and here's the sample at here, right? Here is sample, and you have two bearings at here, two bearings at here. Okay. So this weight is attached at this location. That basically will cause, two downward force loading at this location, at the bearing, these two bearing locations. Because they are symmetric, so you have a W over here and a W over here, right? And this is a supporting bearing here, so you will have two supporting force to balance out, and that gives you another W here, another W here. Okay. So now, if this is a C, this is A, B, this is D location. So I can think about between C and a D location here, right? Think about this between C and D location. Here's a C, here's a D, and here's A, here's a B. Okay, so basically, for this portion, consider this portion of a shaft. Okay, this portion of a shaft here. Now the loading here is you have a W over here and W over here, and then you have half W over here and half W over here, right? Okay, and this is all basically symmetric, right? So this portion is the same as this portion, the length. Okay, so that's basically formulated into the loading condition for this shaft at here, right? It's a shaft. Okay. And if you, in your first tutorial, and you learned, for this kind of loading condition, if you're going to draw a bending moment diagram, if you're going to draw the bending moment diagram at here, okay, so what would it look like for the bending moment? It's 0 at the beginning, and increase up to this location, okay, and then drop it down to over here, right? Yeah. Okay, and if you draw the shear force diagram, and you will see the shear force basically, I'm not sure, let's just see, it's positive, maybe negative here, and it goes to 0, up to here, and here. So this is your moment, and this is your shear force. Okay? Yeah. So if you look at this one, and we have seen this quite a few times now, so for the portion AB, which is the specimen location, the specimen that you're testing, within A and B, what do we call this? Within A and B, this is called what? Pure bending, right? So within A and B, which is the specimen here, you have, so A and B here, you have this pure bending in here. Okay, so pure bending. So which means if you cut a cross section, right? If you cut a cross section between A and B, then along that cross section, there should be only this bending moment here. Okay, bending moment. Is that good? Yeah. So if I cut a cross section, if this is the cross section here, okay, this is a cross section. Okay, and suppose, let's do this, right? Let's suppose this is a location, right? This is A location, and this is the neutral axis. And the whole bar, the whole shaft is rotating at this speed omega, for example. Okay, speed omega here. Okay. Yeah. So think about the detail now. At this A location, so for A location, okay, at t equal to 0. So let's say, for example, right, at t equal to 0, this is A location. And what is the stress at the A location then? What's the stress at the A location? At A location here, remember there's only bending, so the stress at A location equal to what? If the bar has a diameter d here, okay? What's the stress at A location? M times divided by I, right? Okay. So that initially, that's how much normal stress at A location, right? But remember, this bar is a rotating bar, right? It's a rotating bar here. So when it starts to rotate at t equal to the next moment, at any other t moment, the A will be rotated to somewhere else. So A probably will be at this location now. Let's call it A prime. Right? So we're talking about same location here, right? We're talking about same location. It's just at a different time moment, it's at a different location of this cross section. That make sense? Yeah. So at the t equal to t moment, it's at A prime location. Okay, at A prime location. At A prime location, what will be the basically the stress at A prime location? What will be the value of the stress at A prime? Right? So let's say here is initially here and then up to, so from here rotate to here. So this much rotation basically is omega t, right? Omega t. So omega times t, and that's how much angle that it has changed, has rotated. Okay? That's your omega t at here. Right? So at this A prime location, your stress level is basically the same everywhere, which is parallel to the neutral axis, right? Yeah. So if you draw horizontal lines, anywhere along the red lines will be the same normal stress. Okay. And what would be that value? That's sigma equal to what? Still m, right? It's still m, and it's m times this portion now, right? So it's this portion of the distance. Okay. Yeah. And that portion of distance, d times cosine omega t, and then divided by I. Okay. So at any other moment A prime, your stress is this much. Okay. At the top and the bottom, you have the maximum basically, which is this value here. Okay. Yeah. So if you look at the sigma here, sigma refers to the stress for the same location, right? For the same location, because it's rotating. So that's why the stress value for the same location experience a cyclic curve like this. It's a cosine sinusoid or cosine curve like this, right? Okay. So this is basically for the A location here, right? For A location, here's how much stress it is varying as the time goes. So as you can see, at that A location, this is basically, if you recall that, what type of stress or what type of loading we just referred to. This is called what? Complete reverse loading, right? Completely reversed. So this is a completely reversed loading. Okay. So this structure experiment, right? So basically what I'm explaining to you is, with our roll rotating machine, it presents a completely reversed loading, okay, for the test specimen at here. Okay. And the completely reversed loading magnitude is given by this much, which is related to basically the weight W, right? So the M, okay, can be calculated by half of W times the distance at here times this distance, right? Yeah. Okay. So that's basically what the principle of this R roll rotating machine is. It gives you complete reverse loading, and okay, from here we actually will be able to sketch a so-called stress life diagram. So here's what you do, right? Basically, you apply one weight, for example, I don't know, 50 pound or 100 pounds. You subject this part to a certain number of rotations. Okay. Yeah. So basically, you do this. Okay. Here is the stress. Okay. And of course, the stress comes from the M, right? And maybe it's 150 or 200 or 300, right? Up it's going. Okay. So under each one of the stress level, that's amplitude. Okay, that's actually amplitude here. Under each one of stress level, then you observe the experimental results, and you will see, okay, at this level, amplitude is sustained 1,000 cycles, okay, before it cracks. And at that level, sustain 100, right, like this. Okay. So that experiment, basically, if you do multiple experiments, and you'll be able to collect the data between the amplitude of the stress, this one here, and also the number of cycles until it fills. Right. So you put this data together. Horizontally, you plot the number of cycles, the fills, and vertically, you plot this amplitude of stress there. Okay, complete reverse cycle, and then you'll be able to sketch out, okay, this so-called stress life diagram, SN diagram. Okay? Yeah. So this SN diagram is a very useful diagram to use in order to prevent failure from happening. Okay? Yeah. It's very much like the tensile test. You do one tensile test, you got a basically yielding strengths, right? So if you look at the vertical one here, right? If you look at the vertical one here, we call that fatigue strength. So sometimes with notation wise, we use basically SF for fatigue strength, and then we use a associate with a number of cycles that are here. So basically means if I draw a line, for example, maybe let's try this 100 here, and then you go all the way over here, okay, and then you're going down in here. So that basically means the 100 KSI here corresponds to somewhere between 100 and 1,000 number of cycles here. So this is basically 100 KSI corresponding to this is 100, maybe that's, I don't know, 400 number of cycles, right? Yeah, that's a strength. So for that material, basically saying for that material, if you subject the part with 100 KSI, and it is predicted to fail at 400 number cycles. Okay. Yeah. Is that good? Yeah. A second observation, okay, we should also look at is, yeah.
Sorry. Is sigma A equivalent to SF?
Yes. Yeah. This basically sigma A here is the values over here.
Okay.
Yeah. Good. But I need to also emphasize that here, this is basically results from completely reversed loading. Okay. Yeah. Okay. This is a result from complete reversed loading here. And second of all, from this diagram in here, okay, we can see categorized into a different region. One is called low cycle here, and then high cycle. There's also infinite life here. Okay, infinite life. So what this basically means is it refer to the number cycle lower than 1,000 as a so-called low cycles. Okay, so if you feel less than 1,000 cycles, okay, that's a low cycle. And above 1,000, we consider as a high cycle. And above 10 to the power 6, so the infinite number life here is corresponding to the 10 to the power 6. So if your parts can survive 10 to the power 6 number cycles at least, then this is basically, we can call this part has actually infinite number life. Okay? Yeah. Is that good? Yeah. If you look at this data points that are here, and there's an interesting point. There's an interesting phenomenon, which is, you see here. See, after this 10 to the power 6 here, so all the dots here, right? They become what? Become flat. Okay? They don't keep going at here, right? They don't keep going anymore. Okay? This is also this is basically this resulted here at this location here. This is called the knee point. Okay, this is the knee point here. Yeah. So basically, in other words, if your cyclic loading, okay, this is 50. If it's lower than 50, if you have a value lower than 50 at here, what would you expect the life for the parts?
Okay.
Huh? Okay. Infinite, right? Yeah. So this knee point set here, okay, or this value, okay, correspond the value corresponding to that knee point. Okay. So this value here is so-called endurance limit. Okay, so I'll just write it down here. So this knee point produce a value called endurance limit. Okay, and we use SE. Okay, we use SE to represent this quantity at here, endurance limit. Is that good? Yeah. These graphs are typically referred to ferrous type of material. Okay. Only the ferrous type of material will exhibit this knee point. If it is non-ferrous material like aluminum, you actually will see this curve keep going down. Okay, this curve will keep going down here. So, only the knee point only exists for ferrous type of material. Or in other words, endurance limit SE only exists for ferrous type of material. Okay. So, and now that brings to the design now. Okay, so let's briefly talk about design, and we'll look at also look at it very detail here. For fatigue loading, there are two kinds of designs. Okay, the first kind, let's call it case number 1. You design for infinite life. Okay, you design for infinite life. So if you have a material and you want to design for, if you have a shaft, material is picked, and you have a loading condition, and you have it's a fatigue loading, and you're designing for infinite number of life. Basically, the first information you should remember, this is basically designed for more than a million number of cycles, right? 10 to the power 6. Okay. Then, when you design for the infinite number of life, okay, what we do is, okay, let's let sigma A be the amplitude of this completely reversed loading. Okay. So if this sigma A is the amplitude of the loading stress, okay, then here you do have, let's say for example, you probably do have this graph here for that material, right? You do have the graph of the material. If you design for infinite number of life, how do you calculate the safety factor? If you recall from the first lecture, basically you will compare between two values. One is the strains and over the stress. So here you're comparing this SE over sigma A. Because the SE is the value, the endurance limit is the value corresponding to what? To the endurance, to the infinite number of life. Okay? Yeah. So just compare this with the amplitude of the current completely reversed loading. If this is greater than 1, then you're safe. You're basically, I wouldn't say it's safe. You basically you have an infinite number of life for the parts. Okay? For the parts. So if in less than 1, then no infinite life, right? So that's the idea. And second case, okay, so this is the difference, the type of design is different from static loading. You could also design for a finite number of cycles. Okay, you could also do that. And that's also very common too, right? The manufacturer gives you a bicycle. Yes. Oh, they just have to set a bar, right? You know, basically, yeah. Infinite life, 10 to the power 6. It's not a rocket science. Yeah. So back to this design for infinite finite number of lives. A manufacturer gives you a bicycle, right? And I don't think it expects that the bicycle will last forever, right? And you pedal your bicycle, at a certain stage, your crank with the bicycle probably broke. That actually happened to me once. Yeah. So in the middle of the campus when I was at UBC, and then all of a sudden you pedal and nothing works anymore, right? So and the middle shaft actually broken. So there is a finite number of cycles. That's fine. You know, you design for maybe 10 to the power 4 number cycle, for example. Okay. Yeah. So which is okay. So in this case, then what you do is, okay, if you're designing for a finite number of cycles and you want to basically make sure that you are safe or not. So here's a number of things that you have to have, the information you have to have. First one, okay, what is the fatigue strength at this? So what is the fatigue strength at n equal to, right, 10 to the power 4? And of course, if you have these diagrams here, you just go 10 to the power 4 here. Okay, so that's your fatigue strength, right? That's your fatigue strength. Okay. So that's how much it is. Yeah. And now, and the second of all, okay, and then you specifically now. So let's just suppose your amplitude at here is actually 50 ksi. Okay, so you apply a stress sigma A equal to 50 ksi here, and your fatigue strength, if you look at the table, maybe did that go for? Okay. So let's say this is a 70 ksi here. Okay. In other words, you know, your this value is actually lower than this, right? Lower than this. So then you can see, okay, my safety factor is basically okay, 1.4. Okay. So you're safe. Basically, you can achieve these number of cycles under the current complete reversed loading. Is that clear? Yeah. Or alternatively, you could also think this way. So under this amplitude of complete reversed loading, how many cycles would you expect? Would you expect to be comparable to the 10 to the power 4? It should be what? Under this loading. Should it be less than this number, or should it be bigger than that number? Bigger, right? Yeah. And then the natural question, which we'll answer later. So you should see, okay, so if under this loading it will be more than this, then how much, right? So how many number cycles? You know, if they're subject to this amplitude of complete reverse loading, how many number cycles before it fails? Is it 2 times 10 to the power 4, or is it a 3 times 10 to the power 4, right? Yeah. So that's something that we'll look at it in the next lecture, basically. Given a stress, estimate number cycles before it fails. Okay. So that's basically for the fatigue. There are 2 different types of design we're talking about. In most of the cases, we'll look at the first case. Okay, so we're designed for infinite number life. Right? Yeah. So before we move on here, then I also wanted to clarify some notations. Okay, before we go ahead. Right? Okay, so first one, we will have 2 different notations. One is called SF, and the other is called SF prime. Okay. So both of them is a concept of fatigue strength. Okay. It's a Bunsen fatigue strength at certain number of cycles. At a certain number of cycles. And I'll explain the difference between the prime and non-prime symbol. Okay. And second of all, you have SESE prime. Right. So SESE prime, they are all concept of the so-called endurance limit. And endurance limit, as we just learned, this is basically for what? Infinite number of life, right? Or greater than 10 to the power 6. Okay, so now the difference here, you have a prime and you have a non-primed. Okay. So there's SE, SE prime, and there's SF, SF prime. Okay. So the difference is for SE prime or SF prime. Okay, this is a prime variable. Okay. When you see this, they refer to, their values refer to the values that obtained from tests under lab conditions. Under lab conditions. So this lab condition is a keywords at here. Okay, it's a keywords, and when you design, when you do experiments, and you do experiment under lab conditions. So lab condition is a very strict condition. It basically means you will have a standard temperature, room temperature, and the specimen that, as I show it here, the specimen will have a standard diameter of 0.3, and the specimen will have a standard surface finish. Okay. So those are what the lab condition means at here. Okay, the lab conditions. But however, you don't have the luxury to basically conduct experiments every time under the lab condition. And the part, the material, outside, they are the actual condition, right? Yeah. So the non-primed one basically are the values, okay, from actual conditions. So that's the difference between the prime and the non-prime. Okay? Yeah. Yes.
Why would lab conditions be a luxury if the actual conditions would be more precise to what is going to go?
So the idea is, you see here, right? For example, if I want to design for infinite number life, and you're going to have to calculate this safety factor, isn't it, right? Yeah. So the safety factor you're calculating here, it's not a safety calculator, you're based on your lab condition, the value you obtain from the lab condition here, right? The SE at here is the condition, it's the endurance limit probably due to this harsh environment that the parts is being putting under. That makes sense, right? So that's why you need to obtain the actual SE or SF. That make sense? Yeah. So that's basically the idea. We need to obtain these two, right? Need to obtain these two. How do we obtain these two then? So what we do is, we're not gonna, we cannot have an experiment done for one particular, external condition, and then you do another one for another external condition, right? That's impossible. So what we do is, we obtain our SE from the SE prime. That make sense? Yeah. So you have a lab condition results, and then we will obtain this SE based on SE prime. By doing what? By applying a series of the so-called modification factor in front of this SE prime. And we're going to apply Ka, Kb, Kc, Kd, Ke, and Kl. A series of factors here. Okay? And I explain each one of them. And those factors are also so-called the marine factors. Okay? So all of these that are here, we also call the marine factors here. Okay? And we'll look at what do we modify. Basically, what type of condition we modify here. And similarly, your SF could be modified. Okay, basically based on the SF prime. Okay. So from here, then the question here is basically the steps, okay, for obtaining SE and SF. Okay, there are two steps. First step is to find SE prime or SF prime, right? So I guess we just mentioned here, one is you can obtain it from experiment. Okay? So you do experiment, you can get a SE prime, you can get a SF prime. Okay? Yeah. And the second approach is, you may not have the luxury to test on every type of material, or for any type of material with the different strengths here. So then what do we do here, right? We do have a approximation formula. Okay, we do have a approximation formula here to use. I will go ahead and give you one. I think my textbook has a couple more there. Okay. So what we typically deal with the steel, so we'll just write down the steel one in here. Okay. For steel, your SE prime equal to this. So if your SUT value is less than 200 KSI, and you can use just 0.5 times SUT as the approximate value for the SE prime. Otherwise, you can use 100 KSI as the SE prime. And 200 KSI are typically about times 7. It's 100. It's a 1400 megapound. Okay. That's another approach to get a SE prime. This is actually most of the time for calculation. This is all actually most of the time we'll use to obtain our SE prime. Okay. So if you give me a material, first step, look up to find this SUT, and look at the value of the SUT, and then use this formula to find SE prime. Okay. Okay. So I do have a formula for iron, but I'll skip that. Okay. So now let's look at each one of the factors here. Okay, each one of the factor, and how do we modify this SE prime or SF prime? The first factor we'll look at is called a surface factor. Okay, surface factor here. Okay, so let me move up a little bit here. Okay, so this is a table here called a table 6-2 in our textbook. So this table gives us the guideline of how to find the Ka value. It provided 4 different types of surface finish: ground, machined, and cold-drawn, hot-rolled, and asphalt here. Okay. Yeah. So how you calculate this? For example, for ground, okay, your Ka is, so you look at your Ka value. Depends on the material, the unit that you pick. You may be using KSI, you may be using megapop, right? So this is basically what you need to identify it here. So let's say, for example, I'm using the standard unit here. Okay, so 1.58. Okay, so 1.58. If I have a material that is 520 megapop, okay, so let's say SUT equal to 520 megapop, for example. Okay, so then your Ka is equal to 1.5 times this to the power of B to the power of negative 0.085, like this. And you calculate this, that gives you 0.9285. Good. So basically, your Ka value is A equal to times SUT to the power of B. That's the formula here. Okay. Yeah. So let's try another one here. Let's try the machine type of surface. Okay, machine a cold drawn, and this time, what will be the value of Ka now? Okay. Before I give you the value, I want you to take a guess. What do you think the value of the Ka here compared to the ground? Do you think it's going to be bigger, or do you think it's going to be smaller? Smaller? Yeah. Why is it smaller? Because this surface compared to the ground is what? You mean this is smoother than that? Ground, machined, hot rolled, as forged. As this is going down here, you get a rougher surface actually. Okay, you got a rougher surface. When the surface is getting more and more rough, and then what do you expect for the surface? So more rough surface basically will present more potential problems, right? Yeah. And more potential problem basically means it actually will tends to fail more easily. And that basically means your SE value should be smaller than SE prime. And that basically means your Ka value should be smaller. So this one here, you'll get 0.86 here. Okay? Yeah. So when you multiply this Ka with the SE prime, you're basically reducing this SE prime, because SE prime is obtained in the lab condition, right? The experiment, so the test specimen has a much smoother surface. It has generally higher SE prime. Okay? So that's your first factor here. The second one is called the size factor. Okay, Kb size factor. This is maybe the most difficult type of factor to determine here. So I'll categorize this into a different situation set here. Okay. Situation number 1, okay, is for rotating circular shaft under constant bending. Okay, under constant bending. This is the first scenario. So try to envision what this scenario means, right? You have a shaft rotating, and then there is a constant bending applied. Okay, that's actually exactly the scenario corresponding to which one? Corresponding to that what test? Exactly, right? Yeah. So if this is the case here, this is a basically completely reverse loading given to you. Okay. Now if you think about it, for a lab condition, the size is 0.3 inch. Okay, the size is 0.3 inch. So now if you have a different size other than 0.3, right? So your KB, okay, you use this formula to calculate the KB. So D over 0.3, okay, to the power negative 0.103. This is also approximately can be simplified into 0.879 D to the power of this. And that's when D is, okay, between these two values, 0.11 to 2 inch. And if D is greater than 2 inch and less than 10 inch, so forget about this, okay, then you use this formula, 0.91 D to the power of negative 0.107. Okay. If D is greater than 10, you can simply just use a 0.6 for the KB. And this is this one here, this formula here is in millimeter, okay? So this D here, they are in millimeter. So this is actually very important, okay? Sorry, this is not in meter. This is in inch here, in inch. Okay, this formula here is in inch. And there is a separate formula if your dimensions are all given in the millimeter. Okay. Of course, you can convert it, but there's another formula for millimeter. Okay. So look at the lecture notes for the formula for the millimeter, right? Yeah. Okay, for millimeter unit. Before we go ahead at here, so let me ask you a very simple question here. You don't have to calculate. What do you think the KB value is when D equal to 0.3? Well, you can calculate. What's KB value when D equal to 0.3? Huh? It's 1, right? Why is it 1? Because there's no change, right, compared to the lab size. So it should be just 1.
What's that lab size?
Labs the specimen inside you attach to here. So that the diameter. Yeah. Yeah. Second question. If D is greater than 0.3, D is greater than 0.3, what do you think the KB value? Do you think it's going to be greater than 1 or less than 1? When the D is greater than 0.3. Greater than 1 or less than 1 for the KB? Less, right? Yes. So the first one here, it does include some values actually a little bit lower than 0.3, right? So you should expect what the KB is. Huh? Okay, that's situation number 1. And then situation number 2, okay, is you have a stationary shaft. Okay. So shaft is not rotating, but it is under reversed, for example, torsion. Okay. So basically, the shaft is not doing rotating, but the torque is moving back and forth. So in this case here, your KB is the same as situation 1. Okay. So use the same formula for the KB. Situation number 3 is when you have axial loading. If it's axial loading, your KB is actually just always taken as 1. Because experiment basically shows the size, the SE value is not affected when it's under axial loading condition. Okay, if there's any cross-section change. So that's situation number 3. And then there's another situation, basically, okay, number 4. It's a stationary shaft. Maybe it's circular or rectangular. Okay, so the cross section could be circular, could be rectangular, is fine, and it is subject to reversed bending. So if you imagine, if you have a shaft, basically it's not rotating, but you have a bending back and forth like this, right? Back and forth. Okay. So in this case, this is a little bit tricky situation in here. So what we do is we also want to calculate the KB, but we cannot use directly that D. Let's say if it's circular, you have a diameter, so you can't use that D right away. So we use, okay, instead of using D, so we try to find this. Basically, the objective is to find a so-called equivalent DE value. Okay, so I'll explain what this equivalent means. So we have to find the DE value first, then plugging into this KB formula. Okay, so this is your KB formula. I only write a portion of the formula, right? Okay, so we have to find the equivalent DE first, and then plug it into the KB. How do we find the equivalent DE? So this is the idea here. Let's say, for example, okay, we have a circular cross section. Okay. Think about the circular cross section. So circular cross section, you have a cross section, circular cross section, which is like this. Okay. Yeah. But right now, this bar or this shaft is not rotating. Okay, it's not rotating. It's only being bended, okay, back and forth, okay, for this moment here, right? Yeah. So what we do is we look at specifically a region. So here I select 2 regions that are here, and then this is so-called 95%. Okay, so 95% of the maximum stress. So where's the maximum stress? This is the maximum stress that is here, right? So when you're moving closer to the neutral axis, then the stress will be smaller. So you're looking for the place that has 95% of that value. So that's basically the region created over here. Okay. Yeah. So this is non-rotational, right? This is stationary. This is stationary here. And of course, this is your D here, right? This is your D here. Now we compare to the situation. Here's rotational, which is a situation number 1. Okay. For situation number 1, there's rotational here. Okay. And consider something rotational. that has a DE value. And then we try to look at the same thing, 95% of this area. Okay, 95% of maximum. In this case, you draw these two horizontal lines, that's 95%, right? But when it's rotating, what is the 95% of this? When it's rotating, everywhere around the edge will experience maximum, right? Because it's rotating. So 95%, what you do is you basically look at a circle, and then within that region here, this is 95%. Okay, it's 95%. So equivalent to these two 95% together to find this DE at here. Okay, let's find the DE. So you can find the DE by using this approach such that DE equal to 0.7 D. Okay? And this is for circular cross-section. Then you can substitute this 0.37 D into the KB formula. Now what if you have a rectangular cross-section? So here you have a rectangular cross-section here. Then the 95% will be here and here. Okay? Yeah. In that case, you can also do a calculation with DE, which is this much. Okay? And this is H, and this is B at here. Okay? And most of the time, I think we're going to use this one here. Okay. Good. So that, yeah.
D is your diameter.
D is the equivalent diameter.
Yeah, but your D, your only D.
No, D is the actual diameter of the shaft, right? Yeah. So D is actual shaft. You multiply 0.7. That's what you use for the formula KB. That clear? Yeah. Okay, I'll stop here, and then there's a couple more factors, and then we can finish next lecture. Okay? Oh, sure. And as a reminder, assignment number 1 is due this Friday, and I'll post assignment number 2 probably today. 4 o'clock, yeah.